Hi, everyone. Welcome to day 2 of the second lesson of Pert and Nert. And so, yep, lesson 2, Pert and Nert. All right, so we left off here at number 4, and we're continuing Helen's money journey, right? So this was, we talked about compounding. We looked from before. Remember, we talked about the different kinds of compounding. So we talked about like if it was split into two, the 6% was split up into 2. And then and we talked about John, Betty, Joe, and Lizzie. And now we're going to write the equation. And here we go. So AFT is equal to the 500, that's the initial, her principal, and 1 plus 0.06, that's the yearly interest, right? And then it's divided by K, depending on how many times we're compounding it, right? And as to the KT, so that K times T, or that always means multiply. And this is the formula right here on the right-hand side, in case you forgot. All right, and so we wanted to figure out, well, determine the amount of money in Helen's account at the end of 3 years. So we know that T is equal to 3. So notice here is all A of 3, right? Because it's for 3 years. And it's going to be compounded. Now we are going to calculate it 3 times. Once with twice a year, once with monthly, and once with daily. And I like to think of compounding like how many times are they going to pay interest, right? So that's in the bank. If I check, if it's twice a year, that's going to be 2 times, right? Probably once in June and once in December, something like that, right? Notice here that I replaced both K's with 2. And then in the calculator, you get 597.103. So make sure that you try this on your calculator because, you know, every calculator is a little bit different. So please work it out. So try these out and see if you get these numbers. And we just round to the nearest cent because we're dealing with money. And then same with 12 months. So if it's monthly, it's the K would be 12 because it's 12 months in a year. And you're going to plug that in just like that. And you should get something slightly higher, right? Because since we're compounding more, so that's a little bit more interest that we're increasing, right? So that's going to be $5.98 about $1.31 difference. And then from monthly to daily, so daily would be how many days in a year? 365. So that's going to be 365. We're not including leap years in this one. So we're just talking about the typical year. So it's going to be 365. So dividing by 365 and multiplying by 365 because they're going to be paying us every single day with interest. So there's not going to be, you know, every day a little bit more, right? So notice right here, it is more. We get more, just not as much more, right? And if you can imagine, what if we instead of 365 days, we do it like every hour, right? How does that change? Is it going to keep on increasing? But notice that the increasing amount is it is decreasing. It's not increasing as fast. Let's say that, right? And so now we're going to kind of go on that idea and kind of extend this. So now we're going to look at this imaginary bank because there's no bank that will do this. And if you know a bank that does this, please let me know. I would like some in on the action. So imagine that Helen finds a different bank that offers her 100% interest, right? So 100% interest means it's going to double my money. Do you see why there's no bank that's going to do this? You're going to lose all the money, right? Unless the person who's loaning it to you is called, I don't know, your mom, I don't know, or your dad or your grandma or whoever, right? Wouldn't that be nice? You loan them like $1 and they give you $2 back, or you loan them $10, they'll give you $20 back. That would be amazing, right? But that's not going to happen here. So that's what we're imagining. So it's 100%. So what is 100% as in decimals, right? It would be exactly 1. So R is equal to 1 in this case. Okay, and then complete this. So we're going to complete this table. So Helen is we're gonna see how much she accrues in 1 year. Accruing meaning like how much is she gonna earn, right? How much is she gonna like gather? And then and depending on the compounding, right? So we're gonna do a variety of compounding, see which one's the best. If she starts with $1, so she's not starting with a lot, it's just $1, right? But we're assuming the next year, for after 1 year, she should be having $2, right? If we're compounding yearly. And if you notice right here, we did color coordinate this. This green, light green on the outside is that principal $1. And then we have our normal 100% of, that's how much we deposited. We want to keep that money. We're not like spending that money, we're keeping that. And on top of it, what are we adding into it? The interest. So the pink is the interest divided by how many times we're going to compound it. So in this case right here for yearly, it's just one. You know, remember it happens 2 times, right? So it's one now down here below the interest and one here at the exponent. And then the aqua blue one is the time period. So this time period is just 1. All right. And if you notice right here, and then we're going to do this with 2. And we, in class, we kind of extended it all out. And so I know this a lot, and I know that this has to do with money. And so we would normally round to nearest cent, but we're going to actually round to nearest no rounding. We're going to just go as far as we can. We're going to see what this approaches, right? What is this getting close to? And so I actually did on a calculate on the Google spreadsheet, right? So here is our monthly, right? Monthly, weekly, hourly, daily, because it's 365 hourly. Remember, you just multiply how many days we have times 24 hours, right? And then if we wanted every minute, well, 8,760 hours times that by 60, right? And you're going to get 525,600 minutes. Does that seem a little small to you? Right? That's the only number of minutes we have in a whole year. That's it. And in a whole year, we get how many seconds? 31,536,000 seconds. That's it. It's not a lot. That's not a lot of seconds. Make the most of what we can, right? And so every second, right? If you notice right here, this is the amount. And if you take a look at this, what do you notice? So let's see if I can pull this up on my annotate section. So you notice right here, okay, yes, they're all 2s in the beginning, right? And if you can see the bigger these numbers are, these numbers like start getting more like consistent, right? So then here we have all 7s, then and 1s, and then they all like our 8s are consistent, and then 2, and then 8, and then from there on out, it we don't know, like it varies, right? So, but do you see how it's approaching this particular number, right? So the more numbers we're dividing by, this number gets more and more, we get close to this particular number. What if this number is E, right? And we call it E. So it's 2 point, so I wrote it down here. So 2 point, let me clear drawings, go back to my mouse. So it does approach this. So this is E is equal to 2.71828128459045223. Do we really need all those numbers? No, but I thought it was interesting. But it is irrational, just very much like pi. Pi, remember, is 3.1415. This is all I know, 159, etc. I don't have anything, but this is the one way that that one of the teachers at here at Beamer helped me to learn. So he said, well, 1828, that happens twice, right? Okay, and so what happened in 1828? Apparently, Andrew Jackson was elected president then. He was, I believe, going against John Quincy Adams, and had they had their election, and then he was elected president. Okay, that's all I know. I'm not a history buff. There were other things, but I don't want to be wrong just in case. I don't want to have that on record. And then we have here the 45, 90, 45, right? That's the thing about the 45, 45, 90 triangle back in geometry. Remember that? Yeah. So that's our isosceles right triangle. I can't do it here. It's like this. Oh yeah, kind of like this. Isosceles right triangle. Okay, assuming that my index finger and my ring finger were the same length. So that's 45, instead of 45, 45, 90, it's just 45, 90, 45. And then my last one is 23. That was my little touchstone. I'm like, ooh, 23, I know that one. That's Michael Jordan's number. Some of you may say LeBron James's number, but I mean, that is not my generation. So I will say MJ is always first. All right. So yeah, so either way you want to remember that is Michael Jordan or LeBron James. It kind of matters, but I won't know. So that's fine. But this is, that's an easy way to memorize these numbers. Just, you know, your next, when you go to pre-cal, right? You could be like, ooh, I know E. Here is 2.71828182. And you don't want to say 1828, because then that gives it away, right? Like you're learning it a certain way. So you'd be like 1828182845904523. I mean, how many more decimal places you want? But I think they'll be pretty impressed, right? And you don't tell them about how you learned that. But yeah, so it does approach that. All right, and then this is just another way I found online that you can, that it gets calculated. I'm like, oh, this is cool, right? Who knew? And so this is also known as the natural base. And in our book, as you can see, it goes up to 9459045. And then we can just add in our 2, 3 because we know about that, right? And most calculators will not be able to go this far because they can't. They don't have enough, you know, space. All right. And this is actually really interesting, the reason why it's called E in the first place. And just as a little fact there, the Swiss mathematician called Leonard, okay, some people, like a lot of people who don't know call him Euler, but it's not Euler because it does look like Euler, right? But it's Euler. Euler, like you're oiling something, it's Euler. I'm just saying. All right. So if you notice, so basically, if we're saying that this guy in the inside in the parentheses with the 52 exponent, like that is approaching this E, right? And we could just replace it with E and just say it's going to be continuously compounding, right? And they do a little bit of mathematics in here. We're going to jump to this part where it says, this is just a Pert, right? So this is, do you see how this is a much more simple formula? So A is equal to the principal times E, you know, E is the 2.71, you know, the thing that it keeps on, you know, getting really close to that. So E to the RT, to the rate times time. That's it. So you see how much more simple this is? So you can only use this if you see the word continuous compounding in there or continuously compounding, either way, okay? But it has to be continuous. All right, so if you take a look at this one, suppose Helen's investment of $500 in her savings account is compounded continuously at a rate of 6%. How much would be in her account at the end of 1 year and 5 years? So try this out on your own. You can always pause or not, but I would say you would definitely benefit a lot more if you pause it and then try it yourself. So again, we put in the 500 here, E to the rate, which is 0.06 times the time, which is 1. And then you should get in your calculator of 530.92. And for those of you guys who are on Desmos, you can, oh, see, we did it that way. So here we go. So it'd be 500. And then E would be just go to your ABCs, just find E, and it's already programmed in it. You see how it like has a thing. So E to the, we go back, so to the power of 0.06. I'm not going to put in times 1 because I know it's just going to be 0.06 anyways. So here we go, 530.92. So 92 cents. All right. So that's what that's going to look like right there. If you have your calculator, note on your calculator, you want to look for, it should be next to the log. You should have noticed like a button called log and you're like, why are trees in there? That's the thing. Okay, we'll talk about that later this unit. But this is the LN, or on yours, it may look like IN. See if I can find it here. So do you see this right here? That's IN. So the one above that, that's the inverse, which is E. I'm just saying. So you don't need to worry about the LN for right now. Just know that that's where you would find it. It's above. And usually with calculators, they usually do like the inverses, like right above. They're like related to each other. Like see the square and the square root? Related. That's why you see them next to each other. And how do you access these ones up here? Remember with the second button, or it could be for you the shift button. Either way, but usually they are the same color. Like this is shift and it's written in yellow. And so that's why, and then for, where's the natural? There it is. And so that E button is in yellow. Not that you can see that very well, but it's kind of fuzzy. So for you, it may look like IN, but it's not IN, it's LN. Just FYI. All right, so let's take a look here. So you should do the same thing with 5, and you should get 674.93. All right. And oh, also another thing to note, if yours automatically pops up with a caret, that's fine. Just make sure you put parentheses around the 0.06 times 5 so that it includes the 5 within the exponent, or else it's going to multiply whatever you get here and then multiply that by 5. That's not what you want. So that's why we have to put in parentheses. It makes a big difference. All right. And then we talked about this. So of these graphs, 1, 2, 3, and 4, of these graphs, which one is actually not which one? So if we're looking at graph 1 is what I should say. I introduced it wrong the other way on one of the classes. So if it was 1, which one of these A, or actually I don't even need A, B, C, or D, right? I can technically just say the function name, right? I'm such a ding dong. So here you go. So function F, G, J, or K, which one represents that decay? Oh, that's so like rhyming all day long, right? And if you notice right here, it's obviously color coordinated, right? So we had talked about 3/5. And the reason why it's 3/5, and some people say, oh, it's because of fraction. I was like, well, 1.3 is a fraction. I could write that as 13 over 10. Come on, 13 over 10 to the x power. That's still a fraction. Why did you not pick that? And then somebody had said, is related to yesterday's stuff, right? With the first day's lesson, which was that the B, this number inside the parentheses, has to be less than 1. And obviously 13 over 10 is not less than 1. It's 1.3. So definitely not less than 1, right? So that's why it had to be J instead of K. All right. And then for the other ones, how do you know? So if you look at the blue one right here, which of the remaining 3, F, G, or K, would be the one that increases the fastest, right? So you see how the blue one increases pretty fast, whereas like number 4, this one is like pretty slow. It's like a gentle incline, right? And the number 2 is like pretty steep. And people had said, oh, it's 3 because we're multiplying by 3. It's the biggest one there. Like this is 1.3 and that's 2. So obviously 3 would be the fastest one because you're multiplying by 3. Okay, and then that would mean the most gentle one, gentle slope, is K, right? 1.3. And then the 2 obviously is the one that's in between those two. And so my question was, well, what about the L of X is equal to X to the X power, X to the X power, E to the X power, right? What would that be? And people reminded us that some students reminded us, oh yeah, E is just 2.718, right? So therefore, it should be in between 2 and 3, right? That should make sense, right? Because because it'll probably be closer to 3 because 2.7 kind of closer to 3 than it is to 2. So here we go. Here's our graph. So here's 2 to the X power. Here's 3 to the X power. Notice 3, yes, is definitely much more sloped. Notice here at the Y-intercept, it does cross over at just 0 or at 1, 0, 1, because of, why is that? Because remember, anything to the 0 power is 1. So E to the 0 power should be still 1, right? Yeah, it's still 1. It doesn't matter what it is. If you look at it, like see the red line, it is much closer to the 3. It's like that. See, cool. Exactly what we said. So just to show you that E is just a number, right? We can literally graph it. This is what it looks like. E to the, it's in between the 2 and the 3. All right, so there we go. We're gonna move on just a little bit here. So now we talked about Pert. Now we're gonna talk about Nert. Have you seen Nert? So Nert has to do with population. So thus far we've been working with money and with interest, compounding, and all that kind of stuff. But population also works in this fashion, right? And it is continuous because well, why is it continuous? Because birth rates, death rates, all that in general. There's no given time for that. We don't say, oh yeah, our population grows like just twice a year. Hospitals only give birth to children only twice a year. Yeah, or 3 or quarterly. Yeah, it doesn't do that, right? So it's continuous. So this is going to be NO is our, let's see, here's our formula right here. So NO is our initial population. Why they use N? Good question. I don't know. but that's our initial population at t is equal to 0. So at time 0, whenever you're setting like this is our initial point, this is our start time, right? Whatever time that is, that's going to be t equals 0. Then you have your rate, which is, you know, what we've been talking about. Same with your time. And then n of t is going to be our population at whatever that time is, whatever we're looking for, right? That's our predicted population or what have you. So this is how people can predict. Oh, we're predicting in 2030 that we're going to have this. If our growth rate continues, we're going to have this many people, even with like, you know, like the Earth's population, right? It has that exponential growth going on. So here we go. And the question is, well, what about a decline? What if we have a decay, like, you know, the exponential decay? What is that going to look like? And we talked about, well, it should be like a fact, like less than 1, right? So 1 over e. And the way we would show that, because we don't want to write 1 over e here, because that's like not a Nert, right? So remember, if you remember your exponential exponent properties, this is equal to e to the negative 1, right? So that's why we would just put that little negative right there. And that's decay. Done. Happy days. So now if you take a look at this, so we're going to use the formula and figure out, oh, the population of city of Fredericksburg, Virginia was approximately 19,360 in the year 2000 and has been continuously growing at a rate of 2.9% per year. And notice it says continuously. So we're like, ooh, Nert. And please note that 2.9% is not 0.29 because that would be 29%. That's way too large, way too fast. So 0.029. And again, we're going to put our initial population right here, E and to the RT. So R is going to be 0.029 and then to T, we don't know. This is just our formula. All right. And now it says, use your function model to predict the population of Fredericksburg in the year 2020. So last year, I guess. And so if you take a look at this, let's see here. So instead, okay, so don't use the number 2020 in there for a T, because 2020 years did not pass since the year 2000, right? Because remember, we're starting at the year 2000. So from 2000 to 2020, how many years have passed? 20 years, right? So that's going to be here 20, just like that. So we put in 20 years. And then you putting in your formula, your calculations, and then it's going to be 34,577.7. We're not putting dollars because we're not talking about dollars, we're talking about people, right? Then you're like, should we put the 0.7? Usually if it's just a model and we're predicting things and with a formula, that's fine. It's like, you know, on average, people have 2.5 children. Nobody actually has 0.5 children, but, you know, we're saying, oh, it's between like 2 and 3, right? All right, so C, what value does your function model give for the population of Fredericksburg in the year 1920? So what would we put in for T? And so some people are like, ooh, -20, because it's 20 years before the start time, right? Do you see how that works? So then we put in -20, and do you see what we get? A smaller number. Yay. So that's going to be 10,000, what is it? 10,839.6. Happy days. All right, and then it says use technology to estimate the number of years it would take Fredericksburg to grow to 40,000 people, right? And assuming, you know, same trends, nothing has really changed. It's pretty much this trend is going to go on, right? And so here we have, oh look, I wrote it down already. So let me erase these guys here. I'm gonna put this one, and I was like, ooh, it's gone. Where did it go? It's like, oh, I needed to zoom out because it's such big numbers. Come on. All right, there you are. So here we have, we're going all the way to 40,000. So we're trying to predict how much time. So we definitely know it's going to be more than 20 years, right? Because at 20 years it was, you know, oh, there's 4. Oh, that's 4,000, not 40,000. All right, there we are. So notice it's like, it doesn't even look like it's even that far. So I'm getting this to be about, and don't ask why my mouse is up there and the point is down there. I don't know. So this is about 40,000. There we go. 25.2. So about 25 years. So what year would that be? 2025. So about 2025. That's when that's going to happen. We can predict that. This is how people predict things, right? So assuming that all the conditions are the same, there's nothing like drastic that's happening all of a sudden, you know. So probably when this was written, I'm not sure how hard COVID hit them, but you know, that may be that may change these numbers, right? Because when this was written, it was not too long ago, but still, like who can predict yet last year, right? I don't know if anybody predicted last year. So and yeah, so this numbers are probably off, but if we didn't have that, then this is what we would have predicted. So yeah, COVID, that would be another good reason why this model probably wouldn't have worked. But and if you look right here, number one, that's actually the, what is it called? The exit ticket. So if you have not done the exit ticket to check your work, please do so. All right. I will see you later. Have a good one.